Hello, and this is chapter 11. This chapter will talk about SLAM and navigation. These two are very important elements in mobile robotics field. Since you will get knowledges of these functionalities, your robot will have an autonomy during the drive. There are some descriptions for the navigation and the other components. Then we will go to the tutorial on SLAM and navigation. We just skipped a few steps in the previous chapter to run the SLAM and navigation after learning about what are those. So let's get started. SLAM is simultaneous localization and mapping. When even a human is going to go somewhere, it should know where it is now and where is the goal. So to navigate somewhere, the known map should be needed, and the SLAM does make the map. If you are still in trouble on understanding the meaning, let's say pathfinding. Path is a way beaten, formed, or trodden by the feet, persons, or animals, or meaning something else. And these are actually shown in the dictionary. So the pathfinding it's very easy to find the path. But you already know that you need some tools to find the path, even during the travel. Those are the compass and the map. Actually, you can think that these are like ancient tools. Nowadays, the humankind got the new technologies like GPS, smartphone, and they are now able to know where they are and where they should head by touching the screen about a few times. But these ancient tools are intuitive, non-portable device that you can use wherever you are. These tools are very effective in real situation. I guess you can agree with this idea. Even military trainee learns how to use these tools. Nevertheless, they have excellent electronic devices. Okay, so let's suppose that we don't have even those ancient tools. Do you have any idea how to do then? Let's dig into further. Imagine that you are in the dark unknown space. You don't know completely where you are. You don't know what kind of things surround you. But you are going to live in, let's say, a week in the space. You should know where the foods are, and to know that, you should find the kitchen. And to go there, you should know every locations of the obstacles, like furnitures or some home items on the floor. So now, you start fumbling the things that might be placed around. During the progress, you'll guess how much you walked until finding something. When you make progress, you will draw the map in your imagination. Then after that, you will walk around. Of course, there are other kinds of data that will make us walk better, but this is the main idea. And that's the thing that the robot does. If the robot has a rangefinder, and if the robot has an IMU sensor, or something that can help the calculation of autometry, the robot can draw the map. We can define the pathfinding in a simple way. If it is now in the position A, and it's going to go to the position B, during the move, robot avoids the obstacles and the progress will be finished if it gets to the position B. It's very simple. However, to do this, we or the robot should know about 4 elements: position, sensing, map, and the path. It should guess its position, and it should detect the obstacles or the objects. And it should know the map and guess its position by using the autometry or matching the map and the objects detected by the sensor. And if it succeeds to find where it stays, make the path to the destination. Of course, it continues to update the new path, which can be changed from unexpected events or obstacles. To measure something's position, the GPS must be the most known way. But in fact, GPS gives huge errors like few meters away from the real location. So this is not appropriate to the robotics field, especially in indoor. We have actually the GPS in our choice list, but it's very expensive and needs high skill for its use. So there are many ways proposed for indoor locating. The first is to find the colored markers attached to the ceiling and guess the current location. This method is very accurate, so it's mostly used in the factory lines. Although the ceiling should be lower, difficult to manage, set the limit. The second is to use the IR markers. This uses very precisely manufactured markers that reflect the infrared ray comes from the emitter. The error can be restrained to millimeter unit, but it has a problem of cost. The others are to use multiple wireless access points or beacon like a GPS. This does in a very efficient way, but the system is very easy to be influenced by the environment, so the environment setting is very difficult. So we have been used dead reckoning method in a long time in mobile robotics field. A cheapest but very efficient way for pose estimation. It uses the rotation data from two wheels and calculate the move. If you know the data from two encoders, the distance between the wheels and the radius of the wheel, you can just calculate it. This method also has some weakness, since this method is very sensitive on the slip and mechanical cumulative error. This method usually uses IMU data as well and corrects the errors. And this method can estimate related pose, while the other method can estimate absolute pose. So you or the robot should know where it starts moving at the first time. The equations shown in the right side are for position estimation. This is all. The portion is small enough to be processed in the level embedded system. Now let's see the sensing layer. This layer works like fumbling we imagined in previous page. There are many kinds of sensors that can be used here. And yes, we already saw more than a half of these in the previous chapter. The cheapest one in the distance sensor, for example, is about $180, but it works perfect for indoor SLAM and navigation. The next element was a map. The robot needs the map of operating area, but in almost all cases we don't have a map, and even the map data for the robot. Let's say we have the map data, but if the area was collapsed, or if there are so many obstacles that is moving every second, then the map won't do a role. So we should make the map, and the SLAM does it. The last element is making the path and move. There are very hot topics in this field, named as navigation, localization, or path planning, and many algorithms were proposed in these fields. The dynamic window approach, the A-star algorithm, the potential field, the particle filter, and the graph. The DWA and particle filter is used in the Totobot. We'll learn about these details afterwards. So we saw 4 elements. And to summarize, position and sensing can be used for making the map, and we will use the SLAM method to get the map. And after getting the map, the robot can estimate its position and can plan the path to the goal. This is called navigation. So from now, we'll learn about the SLAM and navigation method which are used in the Totobot 3. We will see about the SLAM in the beginning. Currently, the most frequently used ROS package for SLAM is the G-mapping. The feature of this technique is that this uses specific particle filter, and it provides the data on the grid map. This method uses basically the X, Y, and theta based speed command, so the differential drive type robot and the omni-wheel type robot can be used here. What you have controlled in the thermal simulation node in previous chapter was also moved by X and theta speed data. This uses odometry and the two-dimension scan data. If the robot uses 3D depth camera, the data can be reshaped as two-dimension data. These pages show how to install the ROS packages and the firmware of the Togglebot 3. If you have a robot, please try following the guides. What we have launched in previous chapters will run in one computer, but what we are going to try will run in two computers. The one is the computer that you will use to control, monitor the status of the robot, and the other one is the computer inside the Togglebot 3. At first, you will run the ROS core as we did before, and then we will run the ROS launch in the Togglebot 3 SBC. The second line here sets the base model of the Togglebot 3. If you export the burger model will be appeared into the RVS screen. If you choose wrong model of the robot, the RVS and also the other program will not show the test results sufficiently. And after that, run the ROS packages related to the SLAM. And finally, you will control the robot by Togglebot 3 teleoperation keyboard launch. So here, what we'll see is the robot works just as an avatar, and the main process are running the remote PC. Since we won't play the real robot in this class, I will show you how the real robot makes the map in the SLAM. As you can see, the robot at first doesn't have any map data, so the space is very empty. But after moving every corner to corner, you can see the map is being built. The map you are seeing won't be saved as a file, unless you command as save the map as file. You know about this since we already saw the ROS run command for map saver. And now this is the scene, shows the SLAM which uses Togglebot 3 waffle. During the SLAM, you will control the robot basically with your own hand. You can use, for example, the Togglebot 3 teleoperation keyboard launch, or as well as the joypads packages. Here is the details of the map data. SLAM makes 2D occupancy grid map. The pixels in the map data shows the contents in 3 color, which means free area, occupied area, and unknown area. Here shows 3 color, but some SLAM packages show the map even in colorful way. And this is the video that shows the result of Gmapping and the cartographer from Google. The cartographer is told as very robust on moving objects and excellent on map drawing. In addition, development of Gmapping package is almost stopped, so it was told that later in the year 2018, many ROS users who used the Gmapping a while will start using cartographer. These are done in the same space in about an hour, traveling around about 400 meters. So the concept is very easy to understand. And if you want to use these packages to make a robot for a practical way, like service robot, please use what you already have. We will actually see the service robot which used in TotalBot3 package in the next chapter. If you are going to add a manipulation layer on the robot, let the robot run by itself and just stay focused on the work of manipulator. If you want to understand how it works, the source codes are fully accessible through GitHub, which are opened by Open Robotics and so on, so please have a look. So until now, we saw how the SLAM works and what kind of results can be taken. And from now, we'll learn the details of how it works. When the robot runs, the sensor node and the TotalBot3 core node will be active. The sensor node is a LiDAR and publish the scan data via laser scan topic. And the TotalBot3 core node receives the linear and angular velocity data from TotalBot3 teleoperation node. Then the TotalBot3 core node publishes the autometry, and all the TF linked to each other in the TotalBot3 model will be published as TF message describes. Now, the G mapping node draws a map using robots TF and LiDAR scan data. If you think that the map is enough drawn, you will run the map saver node to get the map file, and this file will be used in navigation step. In the localization step, there are many algorithms available, but the Kalman filter is one of the mostly used. It tracks state of an object recursively under a Bayesian model. And another mostly used is the particle filter. In the initialization, particles spread to the randomized field, and then, during the move of the robot, it gathers the data seen from the various state of the object, and the particles converge to a specific point. If the particles converge to nearby a single point on the map, that means the robot is now placed in that location with high probability. The G-mapping ROS package uses this algorithm. You can see the figures, equations, and other details in the textbook. Now we will learn about the second element, the navigation. You need to run the ROS-related programs, as we saw in the SLAM. Only the different thing is, run the navigation launch. We won't play with the real robot navigation as well, so let's check out what the navigation does. The navigation uses the map we saw in the step talking about the SLAM. You can see that the green arrows stick together nearby the robot model. We will dig further into the details in the next chapter, but here this means that the robot knows its location on the map, and the lines drawn in front of the robot means the global path and local path planned by the algorithm. This is another video that shows the navigation of the TotalBot3 waffle. It runs as well as Burger did. The red arrow shows the goalpost of the robot, so the robot will run until making itself as almost the same as the red arrow's direction. So here the navigation uses the dynamic window approach. If you are very first at this algorithm, you may think that the graph on the right side as left axis is something of going left, and right axis is another something of going right. But unfortunately, that's not true. Just imagine the Fourier transform. This graph is drawn in velocity search space, and the red region shows that there are huge regions that the robot can collide something. So the optimization process in the algorithm takes good linear and angular velocity, not the speed and direction. This problem can be shown like this. The robot is going to go to the goal, and there are many choices for robot's movement. The optimization of the cost function will take the best linear and angular velocity, and the robot will finally get to the goal. So from now, we'll run the robot with SLAM and navigation package in the RViz. The dependent packages for SLAM and navigation are the following. Please make sure if you have installed well. At first, run the ROS core. Make sure every time that you run the ROS core before run the nodes. Then we will bring up the tunnelable words in the gazebo simulation space. Meanwhile, bring up the tunnelable model of waffle pie. What we are going to do here is to find out what we can do when we run RViz and gazebo at the same time. The gazebo now shows this scene. And then what we are going to see is the RViz showing the scan data get from the gazebo simulation space. Then let's see how the scan data is changing. Move the robot by using the teleoperation node. As you can see, gazebo world is built up with physics engine, and this affects to the robot's movement. Then we are going to make a map of the tunnelable world we saw in the previous step. This time, use the SLAM node for the map drawing. Then let's see the map drawing via RViz. This result is a map drawn with the scan data in Gazebo World. Now move the robot in entire the world to make the perfect map. If the map seems like nothing more to draw, save the map for the use in the next step, the navigation. Finally, we will run the navigation in the Gazebo world using the map built in the previous step. run the navigation, and see the result in the office. As we learned in the navigation chapter, the robot can't find its position on the map by itself. So we should initialize the pose on the map. Now let's see how the navigation algorithm makes the path and how the robot goes to the goal position.